looks like this. I took this from the web a couple of years ago. I can't remember what the source was. It wasn't Wikipedia as far as I remember. But it's just setting out the value of the call and the put, D1, D2. And if I go back, here we have an explanation of the notation. So the psi here denotes the standard normal cumulative probability, F the futures, X the exercise risk-free rate, lowercase t is the maturity of the option, sigma is the volatility. Okay, and then for the Greeks, because also the black model has its own Greeks, which are a little bit different, we have delta, gamma, vega, theta, and rho. And we could, using the original notation, so I more or less took this notation and then rewrote the notation here for the black model. So we have delta, vega, gamma, theta, and rho, and we've looked at these for the Black-Scholes model, but they're also a set of black Greeks that are important as risk management measures or risk management diagnostics. If we were to estimate these values, okay, we need the probability density function, okay, and delta straightforward to work out, but gamma requires not ND1 but actually the probability density function. Okay, and I've looked at that also in a previous video clip. But we have a set of further parameter inputs of F, K, R, T, sigma. We have these estimates for the delta call, the gamma call, the vega call, the theta call, and the call, the rho estimate for the call, and likewise for the put option. Using the notation before and then just translating it into the notation that I started out with, we have a similar set of options, Greeks. Now notice that the gamma and the vega for the put, are the same. So the call gamma, the called vega, is the same as for the puts gamma and vega. Okay, but theta is different, rho is different, so on. So when we input in the parameter estimates F, K, R, T, sigma, we get different delta, different theta, different rho, but the same gamma, same vega. Okay, so let's look at this in Excel for a moment. Okay, so I've set out the original question, 125. Could take this down a notch. When we generate, that's the original bond price, present value coupons 10, 127.09 is the futures price, and then the exercise 110, risk-free rate 10%, 1 year, volatility 8%, and the value of the call 15, the value of the put, which is generated here, is 12, and then I've estimated the delta, gamma, vega, theta, and rho, and I've also used the estimated probability density function. So this was n apostrophe d1. And just to look at delta here for a moment, it's e negative rt by nd1. And to get the formulas, it's just over here. So the delta e negative rt nd1. And then the gamma here uses this probability density function. Okay, so to estimate the probability density function, if we go back, the PDF probability density function 1 over, if you like, 2 pi square root of that, and then e times we have d1 squared divided by 2. Okay, and we get this value here of 0.0726. Gamma for the call and gamma for the put are the same. So the gamma for the call, gamma for the put, same magnitude. Vega for the call, vega for the put, same magnitude. We can verify that here. The gamma for the call is the same as the gamma for the put. The vega for the call is the same as the vega for the put. The theta, however, is different. Okay, and you might notice here we have a plus, but a minus here for the put, and a positive here for the put, but a negative here for the call. And also ND1 here, but here a negative D1 and negative D2, but N positive D2 here. Also, we might note that we have different magnitude here for the row for the call and the row for the put.